Hello, good afternoon, and welcome to the ZP webinar. So we do two webinars, one of them in the morning, our time just to cover the kind of, I want to say one half of the globe, and then we do this one in the afternoon to cover the other half of the globe. So I've got quite a few colleagues online this afternoon, and we're really going to talk about Djuli. So I've got quite a few colleagues to talk about different aspects of Djuli, but we've also invited collaborators, including customers and also PhD students of ZPs as well, because we want to run through what Djuli is. We want to encourage a greater use of Djuli among our PhDs, but we also want to kind of, I don't want to say train as a bit of a, but also talk to the wider community about Djuli as well. So today's the 8th of August, 2023. And as I say, this is a kind of webinar around Djuli. So let me kind of go forward and also say, look, if this is interesting, we're going to do another webinar similar, but I think we'll also take some feedback as well. And we will also do another webinar on the 4th of September, 2023. Similar lineups, like a few changes, people on vacation, etc. But just to say that if you want to see this again, don't worry. We'll A, put a recording up online, and B, there's another version anyway. Now what I want to do is just run through the agenda and just say, I said here that I'm going to talk for 3 minutes, but I timed myself earlier on and it was wonderfully longer than that. But I'll just introduce Djuli very quickly. We will do a quick demonstration on the interpretation of cyclic voltammetry. We will also look at some data on glucose monitoring, continuous monitoring. So Djuli has lots of great features, can help you in different types of experiments. So we will do that. Also looking at lots of data. What I mean by lots of data is if you want to analyze one piece of data, that's fine. You can use Excel. But once you want to analyze 30 pieces of data, you know, that's really becoming a bit of a problem. And that's what sort of Djuli comes into its own. Also, I mean, Djuli today, we'll talk about cyclic voltammetry, amperometry, and actually we'll touch on impedance spectroscopy as well. So we'll also talk about that. And also, if you're doing something like a PhD with ZP and you're working on some sort of gas sensor, well, how does that gas sensor become a product? And the big picture is we've got something called Sense It All. So I'll introduce it and we will demonstrate it as well. And Sense It All will demonstrate some of the capabilities of Djuli about take a sensor, put a sample on it, get the data up to the cloud as well. And then I'll do a quick summary. So very quickly, this is EP. We were launched 8 years, 10 months ago. We are ISO 13485. We develop electrochemical biosensor and electrochemical sensors. We're in the UK and Norway, quite a large team. Many of the speakers, Sindre, Solran, Lynn are here, and also we have Guyana here as well. So many of the speakers today are in this photo. As I say, we've got locations in Norway and also in the UK as well, including Swansea University. So thank you to April for attending today. I'll introduce Djuli and say, you know, we made Djuli because it was serving a purpose for us. The first purpose it was serving is, and if you're a PhD student of ZP, we would ask you to soon enough to start using Djuli as your repository for your data. So we first of all developed it for data storage, but then it became quite useful for data visualization. So many of the tools that you're using in a lab, let's say you were using a potentiostat in a lab, that software allows you to view your data. But if you want to view it outside of that software, then you're starting to have to use things like Excel, whereas actually, and sometimes you even install software on other instruments, or sorry, other computers. With Djuli, it's a complete cloud-based system. So all the visualization and interaction is actually just through the browser. So there's no need to install software. So it doesn't care if you're on a Mac or it doesn't care if you're on a Windows machine. Data processing, this is when it's getting more powerful. Now it can process data pretty quick. Data acquisition, you'll see Djuli used today to actually run some experiments and the data to immediately go to Djuli. And then API, if you don't know API, it means application programming interface. This is the glue that makes the modern world work, from Netflix to Amazon to Google. These are all kind of API-based businesses. So we didn't want to be left behind either. So we've got an API as part of Djuli as well. I will discuss that a little bit. Also, Djuli is really powerful because if you're a student working in Swansea, Djuli will allow us to look at your data, share and comment upon your data. If you're a collaborator with us in the US, it means that if you give us access, we can look at your data as well. So the modern world is by nature global. Even in the same company, people are not within the same state, and actually having a system where you can just log in and see each other's data is really useful. And the more people that look at the data, the more value you can extract from the data. So Julia does actually answer a question, question number one, where's my data? Well, even within a company, where my data is depends on who's got the data. Some people have got it on SharePoint, or some people have got it on Dropbox, some people have got it on Google. So with a ZP, we gather our data in the lab, the guys upload it immediately to Djuli, and that answers the question, where is my data? And then Djuli is a cloud system, so it actually means that they can visualize it from a desktop, from a laptop, or from a smart device as well, because it's as long as there's a browser, we can deal with it. Next question is, I know where my data is. What does it look like? I just want to quickly look at it. Oh, well, that means I have to install some bespoke software on a device. And I might not even have administration rights on my computer, especially if it's a university computer or if it's a business computer. But Djuli will actually allow you to visualize your data through a browser. So it doesn't require you to do a plugin, even a plugin for the browser. It doesn't require anything like that. So it's great for visualization. Now it's getting more powerful. Now it can analyze your data. So I know we show a lot of cyclovoltammetry today, but don't think this conversation is about necessarily just cyclovoltammetry. It could just be as well impedance and amperometry, lots of ways of measuring electrochemical data, but this is cyclovoltammetry. But it will analyze this. This is something like 8 or 9 different cyclovoltammograms. We can tell Djuli, look at this peak and tell me what the peak height is, and Djuli will find that peak and find the highest point, and then it will give you stats on it. What's the average peak height? What's the standard deviation peak height? What's the relative standard deviation? What's the median? What's the min? What's the max? So we can start getting some simple statistics from it. So people love gathering data. People don't always want to, people are creative. They don't always want to kind of, spend hours analyzing the data. But Djuli, you can just upload it and analyze that and give you all the statistics. So it's kind of having a statistician in the lab with you in some ways. And then it really comes into its own when you're actually starting to talk about a lot of data. And what we can do at ZP is, this will get touched upon by my colleagues as well. But we've got a lot of data here. We want to use it as a quality control. So we can ask questions of the data. Is the peak to peak separation less than 250 millivolts? If the answer is yes, here it's 166 millivolts, then that's a pass. And it'll go through all the data and pass and fail it depending on that feature criteria. We could also ask the question, are my peak to peak separations greater than 6 microamps? Yes is the answer. Therefore, these are passes. So Djuli is able to analyze data, do stats on data, and you can also set criteria, whether this is a pass or fail based on some features. Analyzing data, we can look at signal versus concentration or signal versus scan rate. So not something that we do so much at ZP, but in an academic setting, people love to do cyclovoltammetry, and they like to do cyclovoltammetry versus scan rate. And then they kind of like to graph that as well. And that's something that Djuli can cope with as well. It can say, I've got a series of 4 experiments, one at 10 millivolts per second, one at 20 millivolts per second, one at 50, one at 100 millivolts per second. And Djuli will allow you to label up that data with that scan rate and give you a plot of peak heights versus scan rate. Just for your interest, that tells you that something's under diffusion control. It doesn't matter. I think for us at ZP, what we're more interested in is we develop sensors. So we want signal versus concentration. So we can do that as well. We can say, this is the voltammogram gathered at something like 1, 2, 3, 4, 5, 6, 7 concentrations. They're color coded accordingly. We can see our limit detection is kind of two of these are not particularly well resolved, but the resolution gets better as we get up higher in concentration. So you may end up with data that looks like this. And what we've said is, look at this reduction peak and tell us what the signal versus concentration is. And Djuli will do that and give us a sort of a regression linear fit and say, you know, that the signal is proportional to the offset. The gradient's only negative because it's a cathodic times x, which is the concentration. So we know it very quickly and can calculate the linear fit. This says something about the repeatability of our sensors. These are not just singlet measurements. These are actually triplet measurements. So that says something about the screen printed electrodes that we make at ZP as well. Just a quick heads up, my colleague Lynn is going to be speaking in a bit. And what Lynn's going to describe is how we analyze. Hi, Solran, lovely to see you. Lynn will be describing a glucose experiment where we essentially take a glucose sensor, we put it in a vessel, we get what's called a baseline, and then we add in more glucose and the signal goes up. And the signal goes up, and you'll hear Lynn use things like stepwise. This is like a stepwise addition. You could sometimes call this a titration, but we keep adding glucose and the signal keeps going up. The question you may have then is, what's my sensitivity? What's my signal versus concentration? And Lynn will show you how Djuli can help with that particular calculation. Then there'll be a final or a talk also from Sindra about we use Djuli in our manufacturing. We've got some people from the US. Some of them actually have a very strong background in manufacturing. What makes ZP very different as a manufacturer is we do a lot of tests in our manufacturing process to make sure that the sensors we ship are passing, let's say, our criteria. And you wouldn't be able to do it without a database like Djuli. Last thing, API, application program interface. So even if we're building a minimally viable product with somebody, they may want to present that data in their own dashboard, their own cloud system, and that's what an API allows them to do it. It's the glue between my cloud and your cloud would be an API. So we do have API built in as default. So now I've got a demo, and I will hide myself and say hi to Solran. I want to say good afternoon, but I realize it's good evening. Hi, Solran.
Hey, yeah. So yeah, my name is Solran, and I'm scientist at SUR Peacock, and I just wanted to show you how we would use Djuli just as a tool as a scientist. So I will just pull up Djuli and show you some data that I have been working on. So this is the raw data for some of my electrodes that I've tested in ferrocyanide in different concentrations of ferrocyanide. So it's a redox reaction where you have the oxidation and the reduction peak. And what Djuli is a tool to help you analyze your results. And what I've done in this second curve here is that I've pulled up only the second scan. And doing that, I can go to tools and I can change the states and change the groups. The groups are also automatically updated if I do write my concentration label my measurements with concentrations, then they will be pulled up in groups and they will arrange themselves accordingly. So what I've done here is that I've added a peak fit, which will pull out the highest currents of each curve. And this I have done a peak fit for, as Martin said, where you get a linear regression for these values. So if then you would have a sample of unknown concentration, you can use these this linear regression to find your sample. Another thing that I've been using this exact ferrocyanide measurement for is to calculate the surface of the electrode. Because you have the Randall-Sevcik equation, which is up here. It's just a lot of notes, but it's just explaining the equation really, where it's relating the peak height to the scan rate and the concentration. So if you have an unknown variable, you can find the surface of your electrode. So yeah, it's not only Djuli is not only a place where we upload our data to store it, but it's also a tool which we use for analysis. Like these peaks here, I can download it also using an Excel sheet up here, where I can download analysis results, and it will give me all the values in a tabular form and then Excel sheets. And here you only have 3 curves, so it doesn't. I could easily pull out those values myself. But if I have 100 curves, which I sometimes work with in the lab, it's very convenient having this tool that just does it for me. Yeah.
Great, I appreciate that, Solrun. Now I know that you've got a very important soccer game today. So did that mean that you wanted to go next, or should I go to one of the colleagues?
No, you can go ahead. I think Sindre will take the rest of the, yeah.
Great. Sindre, you all right?
Yeah, I am here.
All right, great.
Right. Cool. So my name is Sindre, and I will discuss a little bit about how we utilize Djuli for sort of bigger data sets. I'm just gonna find the correct screen to share and pull up my Djuli report. So first thing I want to say about Djuli reports, you can see that it's sort of built up like an electronic lab book. So you have all these fields. Some of them, have these asterisks, making them mandatory fields. If not, they're going to be stored as a draft. So that's sort of how we discriminate between like complete reports and not. So that's pretty useful for record keeping, and also a little reminder to the operators to actually keep on filling in the details. Okay, so I'm going to collapse all these fields again and focus in on the data. It's more cyclic voltammetry, but the difference here from what Solrun was showing is that here we have a lot more data. This here represents a manufacturing run that we do routinely at Simmer and Peacock, where we fabricate different types of electrodes. In this case, it is an old batch of sensors of carbon screen printed electrodes, where we map certain features with respect to their positional dependence or position on an array. So we lay these out on an array. Martin showed it in one of his slides. In this case, we have a 4x13 array wafer. We take these features. In this case, it's the cathodic peak height. We extract them and we place it according to their space coordinates onto these wafers. The space coordinates can be manually assigned. So I'll go into tools and into my files, show all my data lines, and show mapping. So you can see these coordinate notations. Or they are extracted. If you're smart with your naming, Djuli can extract that information from simply your trace name. So that's one way of being efficient. Okay, it can also extract concentrations and that kind of thing. All right, so that saves us a little bit of work. Okay, so now let's look at the results. We have our heat map, which where the different colors represents how far are we away from the batch average, and the average is denoted here, negative 1.79 microamps. And then these, we can see the color distribution, whether we have any kind of positional dependency. For example, we have this blue guy over here amidst all these red colors. That indicates something is off. You know, it's almost 100% deviation from the mean. So let's investigate further. All right, so when I look into this data, I can see one that's clearly not following the pattern of all these others. And the operator has also been good enough to label it as bad. Therefore, we are two people making the same observation. This is clearly bad. It could be a bad contact, bad coverage of electrodes, or even a discontinuity on the electrode tracks themselves. But it's out of family, so it doesn't represent the batch as a whole. So I can, as long as I justify, take these guys and remove them from my analysis. And that produces a more, let's say, a rich color diagram, because now I've shrunken down my full scale, and therefore variations, tiny variations, will show up as more colorful, let's say. But now if we look at the statistics, they look a little bit better. I have my overall distribution where I have no outliers, really. And if I look at the column and the row distribution, the standard deviations all kind of, you know, match. They're still a little bit higher than I would like, but nonetheless, we've managed to eliminate an outlier. You can do this type of analysis with virtually any feature. I happen to choose the peak height of the cathodic peak in this example, but you could do the position or take the area under the curve, or any of the other features that Djuli supplies. So that's a little bit about how we do mass data analysis in Djuli.
Thanks, Sindre. So I think, I know our next speaker is Lynn. Lynn's going to describe a different type of experiment and use the glucose sensor as the example. So thanks, Lynn.
Cool. Can you see my screen?
Yeah,
right.
Perfectly well.
Okay, great. So as Sindre and Søren introduced, so first step is always uploading your file. The section I'm going to discuss about is the continuous data, which is commonly used for the glucose, or sometimes we use that for the gas detection, especially oxygen detection. So the technology we use at the moment is the chronoamperometry. So after we upload the files here, we can choose the method. So for this method, we know we are using amperometry method. So in the drop-down box, we can just choose an amperometric method. But for example, if you are using the pH sensor, you can use a potentiometric method. So after you select the amperometric method, you will have a window, a tab pop up saying AC, which is the amperometric method. Underneath this tab, we have a selection of tab we can play with. So the most important thing is to do the analysis for your data. So I just close this window and show you what we already processed. So this is an example of the raw data that we collected in the lab. That is our ZP continuous glucose sensor we use in body. So we are trying to understand whether we have the enzyme issues, or like whether the old enzyme is performing the same as a new enzyme. So the way we do the analysis is to do a stepwise analysis. So we add in the glucose stepwise from 0 millimolar, which is a PBS, and we increase the concentration at 2 millimolar step until we don't see the signal increase. So in this analysis bar, what we do is we configure this event. So we know when we increase the concentration. So there are two ways to do it. One way is you hold your cursor here until it appears the gray bar. But my personal preference is to add a concentration in using the plus bar, so I can tell it like where I want my measurement to be. For example, here I measure it in 550 as the next step. So I know the next step after the 4 millimolar is a 6 millimolar. But you can see that like I'm not quite precise in where the measurement is. What I can do is I just move it slightly higher to 550. And then this bar is appearing slightly high concentration. So that is how we do it. And also we are doing the moving average evaluation on the measurement. So we can just increase the window to 50 to include more data point for the averaging. But at the moment, 25 is enough. So I just leave the measurement here to be my next step, glucose spiking in concentration. And then I click on done. And then when I close this window, you will see there will be the actual concentration add on into my plots. If you compare the raw data versus my process data, you can see that like my process data, I bring down all my offset to 0 so that I can have a fair comparison visually to see like what sensor is better performed. And also in your tab, you will see here, it allows you to see extracted value and independent analysis. This one is extremely valuable when you are forming the report, especially when you are doing the FDA report analysis, or you need to have a quick lab book feeling. So you can just click that stepwise analysis so that these results will show up. It will indicate how spread your data is of a one batch, or like how good your standard deviation it is in one batch of a sensor. And also it will produce you the average sensitivity of this batch that allows you to understand the limit of detection. So in here, you can see the limit of detection is 1.98 for this batch of sensors. So you can use that straight to fill in your report. And in terms of independent analysis, it will tell you the sensor performance of individual sensors. And you will see the LOD judging from the linear fitting and the limit of quantification and also the individual parameters. After that, we also allows to look at the stepwise analysis of individual sensors. So that is most of the features we can do. If we want to also include your pre-fitting, you also have this option available to you. You can use the pre-processing to fit your baseline so that you can have the common baseline. Or you can, if you can see the window open, you can also choose the noise cancellation, because sometimes you have a really noisy data, but you still want to extract useful information for your next step. So that pre-processing allows this function to be available to you. Yeah, I think this is most of the features you need to explore for the chrono amperometry. So that is everything. Thank you.
Thanks, Lynn. So I think next we're going to have Sindra. So it's fair to say that we've so far talked about cycle voltammetry, we've talked about amperometry, and now we're going to do a quick bit of impedance spectroscopy. Then it'll come back to me for a quick introduction to Sense It All, and then we'll do a live demonstration from Ghana as well, measuring ginger all. So thanks, Sindra. You're on mute, but no probs. It sounds better.
Thank you. And my screen is visible to you?
Yeah, perfect.
Excellent. Okay, so EIS, or electrochemical impedance spectroscopy, is a technique that is being more widely adopted in the sensor space. I think historically it's been mostly used as a characterization tool, or a way to sort of mechanistically explain your electrochemical system. Nowadays, this technique is more and more available on, say, portable devices and low-cost devices, and we are able to use it for analytical purposes. So that's an example we have here. It's worth saying that in Djuli, we try to make the experience as, let's say, the least cumbersome experience for the user, meaning we don't require additional input for electrochemical impedance spectroscopy, as other softwares would typically kind of require you to, for example, input a model for your equivalent circuit, which is one way of understanding your electrochemical impedance data. We also don't require initial values to be supplied, because that's also required by a lot of these already existing algorithms. So we're taking away a little bit of the sort of expert requirement. You can still, if you wish, supply your own circuit. So I'll just go into settings, show you what that looks like. So pretty standard circuit notation, brackets for parallel and unbracketed for in series. And then we can supply initial guesses for our components. If I sort of change one of these components to something else, I don't know, maybe an R, then the parameters that are relevant will then appear with our desired units. So if you very much wish to supply your own initial guesses, you're welcome to. You don't have to. So we call it circuit fit, and let's have a look at what that looks like. So we have our typical representations. We have our bold plots representing both sort of the overall or the absolute impedance versus frequency, and the phase angle versus frequency. I've already pre-populated concentrations here, so they are color-coded. And in this particular instance, we're trying to make a prediction model for a particular pathogen. So I've just written down pathogen as sort of the thing we want to predict in units UI. Here we have our Nyquist plot, where we plot the real versus imaginary components, and all the dotted lines here represent our actual measurements, and then the dashed lines is our model. So sort of visually looking at this, our model seems to be fairly good at explaining the data. So we'll leave it at that. And then I can verify that by looking at these performance parameters for our goodness of fit. So for each data line, we have both these of average error and the chi-squared value, which tells you something about how accurately are we actually hitting our real data with the supplied model. Okay. And since we're a sensor company, we don't stop there. We actually want to extract the parameters of the model at different concentrations, such that we can make a model out of, say, one of these parameters, or several in combination, if you wish, to predict our chemical concentration. So this is summarized in this plot. We call it a parameter plot, where we have all our parameters. So these are properties belonging to these components. And they are then plotted versus the actually measured or the concentration that we know, or the quantity rather, and the prediction that the model comes up with. This is also in table form. So for each component, we made a model. It has a certain goodness of fit. It gives you certain detection limits, certain uncertainties, and so on. And then here, this is a visual representation of that. So if you want to sort of hone in, or we can sort of, by method of elimination, perhaps just see how well or how bad is this fit. We can look, see if we can identify trends. Of course, if we hit, the same number on each axis, that's the best. For me, looking at it, doesn't look super convincing, but that's also an important finding. All right, we're all scientists, so we know we have to explain why something also doesn't work. But if we're going to add a little bit of goodwill, maybe R1 shows a little bit of a trend. If we sort of glance over the fact that 0 overshadows my 10,000. But then again, this is a logarithmic scale, so sort of trying to sort of linearly interpolate this can also trick us a little bit. Okay. Yeah, you can also upload pictures, so that's useful. Picture of setups, picture of recipes, or whatnot that might not sort of fit into your standard data formats. And then if you have any other kind of questions that might not be covered here, we have a question mark at the top. It will bring up a sort of contextual help menu we call learning mode. And then if you hover across certain items, such as the files, it will tell you what kind of file types are supported, etc. If you can't find your file type here, you're welcome to submit a feedback in the feedback form, and then we will try our best to accommodate. So I think I'll leave this at that.
Yeah, thanks, Sindre. And I think thanks for highlighting that form as well, because we've got at least one PhD candidate with us today. So if they're struggling, I want to get all our PhD candidates or students onto this system. And if you struggle, use the feedback form as well. What I'm going to do next is I did have one of my slides said, look, Djuli's great for data storage, data visualization, data analysis, both small data analysis, but also large scale data analysis in terms of manufacturing as well. I'm just going to just play a video that will run in the background, and I'll start clicking the screen, because what Djuli's really good at as well is it forms part of what we call a sort of minimally viable product. So a minimally viable product for us is somebody has an idea, it's some form of sensor. So we have the sensor, and we also have the electronics. So this is a fully functioning potentiostat. We don't necessarily call it potentiostat because most end users, and by an end user I mean somebody in the food testing industry, somebody in a clinical setting like a nurse or a doctor, they don't want to know what a potentiostat is. They want to know that this is the X meter or something like that. So, but we do have this platform which involves electrodes and sensors, electronics, app development. So we have if somebody's with us today and they said, right, I need an app that's fully branded for my application, they can download it off the Google Play Store, and with a simple QR code which they can read off their smartphone, it will reskin the app and make it specific to them. So we've got this kind of idea that people want to get to products very quickly. Most products in the sensor space these days should actually have some elements about them. There should be a sensor element about it, there should be the meter element about it, there should be the app element about it, and there should be a cloud element to it as well. So you take your sensor, you put your sensor in your meter, you put your sample onto the meter. The app tells the meter what to do, and the meter gives the data back to the app, at which point the app will give you a result. So Ghana will do a quick test on a molecule called gingerol in a bit. But then the app will also give the data to Djuli. So the person gets the data on their phone, because, if you're doing a quality control or you're in a hospital setting, you don't want to go to the cloud and log in to get your result. You want the result there and then. But especially for developers and startup companies, etc., you do want the raw data because it's a way of actually doing quality control, make sure things working okay. And also if there's a discrepancy or somebody sort of challenges the data, you can always get the raw data back. So it's a very unique platform like that. So meter, app, sensor, Djuli, and the data. Now what I'm going to do now is I'm going to stop sharing my screen and essentially go to my colleague Gana, who's going to do you a quick demonstration. So thanks, Gana.
Hello everyone, I'm Gana. I'm an engineer here in Zimmer & Peacock. I'll start with the demonstration of our Sensitol platform. So here is our Sensitol meter. It's really small, it fits in a palm. And all we need to do is to connect with micro USB cable. Yeah, and I have an app already installed. I have gingerl sensors and some solution. Now let's put the sensor inside the device. Yeah. Now what we will do, we will connect the device to phone. For that, I need to press the Bluetooth icon and choose the device. Now it shows that it's connected. Then I'll need to scan the QR code, which will tell the app which sensor we are using. And now I can also change my cluster and test name, which are the cluster and test name that are going to go to Djuli. Okay, everything is ready, so I can start the test. I'll press go to say. Now it's asked to set the dilution factor. So this solution was prepared from ginger shot and mixing with 10 dilution factor with the buffer solution. So I'll just apply 50 microliter of this solution. Yeah, and I'm making sure that I'm covering all electrodes. And pressing start measurement button. The measurement will take approximately 30 seconds, and what will it do? It will run the measurement and send the data to Djuli, where it will get the analyzed and send the results back. And once everything is done and everything will run smoothly, we will see the results in the results screen. So 7 more seconds and we'll see. Yeah, it says that it was uploaded and we are getting 2,100 micromolars concentration of gingerol. Now I'll show how the data looks in Djuli. Yeah. So I'll just need to update so it can see the latest results. So here is my latest test. I'll just click on it. Yeah, and here is how our data look like. We are using one of our these peaks to detect the concentration. So yeah, I think that was it. Thank you.
Brilliant. Oh, thanks, Gan. I appreciate that. To be fair, you know, you make it look so simple, but ZP's been developing this technology for really day one. So this is a good, you know, and even before ZP was started, Sindra was working on this. So we're kind of 10 years into this. So that's seamless. Ghana does a test in the lab and the results end up on the cloud. So simple to say, but actually a long time coming, but really worth it now that we've kind of got here. So let me just summarize what we've covered today. So I did a quick introduction to Djuli, data storage, data visualization, data analysis. Actually, it can also do data collection, and it's also got an API, so we can get the data out of Djuli into whatever dashboard you want. We use it for doing things like the analysis of our cyclovoltammetry, you know, voltammetry versus concentration. But we also use it for what we call continuous data, continuous glucose monitoring, CGM. It's a $10 billion industry. That should be enough to make you think this is relevant or interesting. and we use it to analyze those kind of sensors. Also, why I think that ZP is a really good partner just on the production of electrodes, but maybe also production of biosensors. And underlying that is the repeatability of those screen printed electrodes. Where does that come from? It comes from the amount of testing that we do, and the amount of diligence that we've built into sort of say, this is the CV, does it pass, fail? These are the criteria, and we can automate that data collection and analysis really quickly. We're not just limited to voltammetry or amperometry or open circuit potential. Sindre also showed it could be used with impedance spectroscopy. And then we sort of said, look, there was this concept called sense it all, sample on sensor. Data goes to app sends data to Djuli, and then Ghana was actually able to show you that in real time, that it's a seamless kind of workflow these days. So I think that's the sort of summary of what we've talked about today. I can see that we're 44 minutes and 7 seconds into this. It's a 45-minute webinar. What I'm going to do is we've recorded this, so I'll send you out an email of this recording so you can kind of watch it. If you are a PhD student of us or a collaborator of us, you can expect to be using Djuli through the collaboration. And if you're a PhD student, you can also expect us to be sort of saying to you, right, time to start putting the data onto Djuli as well, because the more of us that are using Djuli, the better it gets. So I want to say thank you very much for attending. Thanks so much to Solron and Guyana and Lynn and Sindre. And thanks particularly to the guys in Norway, because I appreciate it's quite late there. Okay, thanks. Take care and speak to some of you soon. Thank you very much. Bye-bye.